Alright, so we have a steel coat hanger. We bend the coat hanger 0.2 meters when we move it back and forth. And we're going to repeat this 50 times. So when we bend the coat hanger once, we're going to assume that this is sort of a spring in a sense. And so it's going to store elastic energy equal to 1/2 kx squared. And when we plug in our numbers, that's going to be 1/2 times 100 times 0.2 squared. And that actually ends up being a plain 2 joules worth of energy. Yep. So now we want to know how much energy we're storing in the coat hanger when we bend it 60 times. So we take 60 times the 2 joules we had before. Basically, a lot of people panicked when they read this question. Do me a favor, before you think about, oh my goodness, here's a formula, we haven't seen it before, what do we do? If I'm going to make you do something a little bit kind of to stretch yourself on a test, please understand, I'm not going to make you reinvent the entire laws of physics or whatever. I'm going to try to keep it really simple. Like here, you've got an energy here, and what I'm saying is, hey, so you're going to create this, and not create, but you're going to put this energy into the coat hanger, and you're going to do this exact amount of energy into the coat hanger 60 times. So in other words, you're just going to take 60 times the 2 joules you had before to figure out what the total energy is that you're putting in the coat hanger. Okay, so this isn't a formula on a formula sheet. It's just based on reading this question and the information you have here. It's a reasonable thing to ask in a high school physics class. So here, assuming only the top of the coat hanger gets heated up, and we're going to say about 0.5 grams, and this is its original temperature, we want to know what the final temperature is given this specific heat. So Q equals mc delta T. And of course, the big question is, what is Q? Well, Q is exactly this energy that we put into the coat hanger by bending it. That's why, in real life, you felt the coat hanger get hot. So we have 120 equals 0.5 times C, which is 0.49. And then our delta T, let's be clear, that's T final minus T initial. I think I should actually put that on your formula sheet, and I will do that. So that's going to be T final minus the 18 degrees we have here. Let's be careful in how we do our math. So I'm going to have 120 equals, this is going to be a big number. I should have thought about that, but that's okay. That's going to be 0.245. I mean, the final answer is going to be a big number. This is a small number here. Times T final minus 18. Don't FOIL anything out. I'm going to divide both sides by 0.245. All right, there we go. This cancels. Whoops. So 120 divided by 0. Yeah, I'm getting 489 here. So when I actually work this out, I'm going to end up getting about 500. Actually, I'm 489.8. So when I actually round this out, I'm actually going to end up getting T finals about 509 degrees. Is that right? 508 degrees, sorry. And don't get all salty with me when you're like, well, I got 507.8. You know what I mean. I know what you mean. We're all friends here. Okay, so 508 degrees Celsius. That's the final temperature. That's a really hot temperature. It's like 5 times the boiling point of water. So let's be clear. I think if we're bending a coat hanger this much and getting this amount of heat into it, I think actually there's going to be just mechanical stress that the thing's going to snap in two before you're even able to get it to this temperature. But it illustrates a good point. So that is question number 4.